So the first speaker at this morning session is Vikki Meadows from the University of Washington on main themes in astrobiology.
Okay, hello everybody. So I'm Vikki Meadows, University of Washington, member of the Nexus and VPL teams. And I was given this huge task to do an overview of all astrobiology themes that might be relevant. So I'm going to try and do my best to focus in on what I think you should know and kind of the backbone of this entire conference, how it's structured, essentially the main themes that we're going to talk about. So what is astrobiology? So astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. And the criticism we often get in astrobiology is, oh, well, you know, this is a topic, you know, a subject looking for an example to study. And it's like, well, we don't actually need aliens to do astrobiology. What we're trying to do is figure out how we search for life in the universe. And that is a very rigorous science. We're essentially putting very rigorous science bricks into a pyramid that will ultimately lead us to the search for life elsewhere. And so astrobiology, to do that, to build that pyramid of what we need to know to search for and interpret what we see, we developed an interdisciplinary system science that encompasses studies of the interactions between physical, chemical, biological, geological, planetary, and astrophysical systems as they relate to understanding a bunch of different themes. And those main themes are how a planet develops and maintains habitability. So we can do that without finding aliens. Because really all that is based on our understanding of the physics and chemistry of water at some level. That's what we're trying to build towards. So that's something we understand fairly well. We don't need to necessarily have aliens. We want to understand how an environment transforms from non-living to living systems. That is a magical process that I am not an expert in, but we have experts in that here, and so we're going to hear a lot about that tomorrow. How life and its host environments co-evolve. We know that life is essentially a planetary process and it interacts with its planetary environment. We will need to understand life and its interactions to be able to interpret the eventual habitable planets that we find. And then how life impacts its environment in potentially measurable ways. So how is it that we, looking through a telescope at a planet 10 parsecs distant, can actually tell that there's life in there? How does life actually modify its environment in a measurable way? And the great thing about astrobiology, and I think one of the main themes of this conference will be, or this workshop, will be that really pretty much everything is relevant. So to address this incredible question of, is there life out there? Are we alone? We are going to need the expertise from everyone. And so studies of the sun, the earth, other solar system planets, our engineers, our telescope builders, all of these people who will enable our measurements, all of this work is going towards informing the search for life on exoplanets. So since this is a Sagan workshop, I also want to thank Carl Sagan. Obviously, he's not here. But he was really a pioneering astrobiologist. And you may not be aware that he really was highly regarded in the planetary science community. He was in so many different areas and fields that we now see as sort of mainstays of astrobiology. He looked at the formation of organic molecules and organic chemistry in comets, in Titan-like environments. He tried to understand what was happening on Triton's surface with organics there, looking at laboratory astrophysics, aerosols, inorganic compounds, looking at tidal effects in the hydrocarbon seas of Titan, Mars cratering records, looking at the early atmosphere of Mars, greenhouse effects on Mars and Venus, SETI, the search for life on Earth using the Galileo spacecraft, which is one of the funnest papers I've ever read. If you've never read that, Sagan et al. 1993, is the Galileo team on a flyby of Earth, looking at the Earth and trying to figure out if it's inhabited by pretending that they know nothing about it, okay? So it's a fabulous paper to read. And then finally, things like impact delivery, anthropogenic effects on the environment, all that kind of stuff. So Carl really worked in all of these different areas and really legitimized a lot of the science that we do today. And so I don't know if you're aware of this diagram, which was for fun. It's a Hertzsprung-Russell diagram of astronomers. And so what we have on here is we have sort of Google hits on here. So this is your net fame rating. And then we have peer-reviewed scientific papers on this axis. And you'll see that Carl is basically over here up in the media stars indeed, but also very close to the academic giants. So I just want to point out that, as famous as Carl was, he also was this amazingly rigorous scientist who has really made the foundation of this field. So I think it's very appropriate that we're having a Sagan workshop on this topic. So on to astrobiology. Astrobiology, we ask a bunch of very fundamental questions. So how do we identify a planet that is more likely to support life? And the simplistic answer to that is that we want to try and find a terrestrial planet in the habitable zone. Okay, and because we're astronomers, and of course European people don't at me, but we're trying to find surface liquid water. That's essentially what we're looking for, because we want a chance to be able to see the biosphere that is interacting with that surface liquid water, making its imprint on the surface and the atmosphere of the planet. So terrestrial planets with rocky surfaces are more likely to support surface liquid water, which increases their chance of habitability and life. So that's kind of what we're looking for. We're at a very exciting time in the field because we now know that there is evidence for an exoplanet terrestrial class out there. We are now observing bodies with sizes and masses and densities that are consistent with the terrestrial planets in our planetary system. And we're also seeing from statistical studies that in fact they may form a distinct class from these sub-Neptune planets that are so common that we've also found that have larger gaseous envelopes. So we live in an era of a zillion terrestrial planets out there. So terrestrial planets exist. Then we say, well, let's simplistically put it in the habitable zone, which is defined as that region around a star in which an Earth-like planet can maintain liquid water on its surface. Emphasis on Earth-like. And the translation of this definition, really, what we're trying to get at is that region around a star where life's requirements are most likely to be met and be detectable. That is the point. And so a lot of people get bent out of shape about the habitable zone, and I think Stephen's going to talk a little bit about how bent out of shape we can get. But the main point, the thing you kind of have to remember about the habitable zone is it's really a probability density for habitability. Yes, things could be habitable on either side of it. Things might not be habitable interior to it. But the probability that things are at the right temperature and that we have liquid water is higher in that region. And I just want to point out this diagram, which I made Sunny Harmon put together once, because I said, I'm just wondering, all these definitions of the habitable zone, people are saying, oh, that old habitable zone, you can throw it out because I've got this definition now pushes it all the way to Mercury. What we did was we overlaid all of the habitable zones from 3D GCMs and 1Ds and whatever, and this is what you get, which is kind of this probability density function. And even though things could potentially be habitable under certain conditions out here, I know I'm going to first start looking over here. I'm going to start looking where everything overlaps and where we think things are likely, despite the conditions, to be habitable. So the habitable zone, really a probability density function, a place to start the search. It's not a benediction. If you're in the habitable zone, you are not automatically habitable. So we're finding planets in the habitable zone, and especially those orbiting nearby late-type M dwarfs will be best for long-term characterization. So we're looking at things like the TRAPPIST-1 system here, and also Proxima Centauri in the radial velocity side, direct imaging side. And so we have these planets now that we are finding, and so there's a slew of them that are potentially in the habitable zone. But again, just because you're in the habitable zone doesn't necessarily mean you're habitable. And these are simulations that we've done within my group. Where Andrew Lankowski published this paper, where we essentially changed the atmospheric composition of the planet in the habitable zone. It's the same planet, we just changed its atmospheric composition, and you end up getting a whole slew of surface temperatures from 237 to 689 Kelvin in the habitable zone. And so certainly some are habitable. This is sort of habitable temperature ranges here. Others are much colder and much hotter. And again, it depends on your composition, which depends on your evolution. And so there are many factors that affect whether or not a planet has liquid water. So habitable zone, kind of a good first cut, but we now know that there are all these, and this is a major theme in astrobiology, there are all of these factors that affect whether or not a planet is habitable. From whether or not it forms with an initial endowment of water, and I believe that Sean will talk about that, the evolution and luminosity and activity of its star and what that does to the water it was originally given, whether there's ocean or atmospheric loss, and then, of course, biogeochemical cycles or biological interacting with the geological cycles of the planet to essentially change what's going on. So even life can modify the habitability of a planet as well. And so if you look at all of the factors, or at least all of the ones that we can think of right now, there are a lot of different characteristics, processes, factors, and evolutionary processes that go into habitability. And so this is a main theme. The habitable zone is really a two-dimensional slice through an n-dimensional space. And all of these factors are there. So, I don't care what people tell you. They can say, well, that planet's habitable. But until you have the measurements and the observations to confirm habitability, you do not know. All you know is it may have a higher or a lower probability of being habitable. So only observations can confirm habitability, and even those observations are going to struggle, okay? So But all of the study of the things that affect habitability and the probability of whether something's habitable, that's fantastic for target detection. That's fantastic for down selecting what we want to go and get detailed observations of. Another major theme is that exoplanet terrestrials would likely be very diverse. And so we're looking at, not just a puffy hydrogen-dominated thing, but a planet with multiple phases and different compositions, which will depend on its star. It will depend on the planet formation and migration processes, interior outgassing, the history of planetary and stellar interactions, geochemistry, atmospheric loss, photochemistry. All of these processes will change the environment of a terrestrial planet. And so we expect a massively diverse population of terrestrial planets out there. Terrestrial exoplanets will also likely support secondary outgassed atmospheres. So the interior of the planet is important for understanding its exterior. So the thing that we will see, the atmosphere, will be a product of what's going on inside the planet. So the initial composition, subsequent stellar surface, interior, and atmospheric evolution will actually affect the atmospheric composition that we see. That may sound daunting, but it also means that we can, by observing that atmosphere, get back at some of these processes. We can look at the atmosphere now and infer what the evolutionary history was. So some of these processes that were on that big scary diagram, which we call planets are hard, the one with all of the different factors that affect formation and migration, for example, of the planet may affect whether or not it has enough water to deliver, water delivered to it. And Sean, I'm sure we'll go into more detail on this. So for example, the TRAPPIST-1 planets are in a resonant chain. This is a dynamical structure, but it tells us they migrated from further out, from more distant birth orbits potentially. They appear to have lower densities, so there's some updated numbers on that now. So we are looking more towards terrestrial type densities, but still far more water rich than planets in our own solar system. And so the densities and the migration suggest that these planets may be far more water rich. So that's interesting. We're looking at more water rich types of terrestrials. I want to point out that terrestrials experience stellar, geological, and atmospheric evolution. This will be a theme also throughout this workshop, and we have several talks on that today and I think tomorrow as well. And so I usually show this in public talks. I say if you think of, Earth is the kernel of corn in the solar system, and Venus is the popcorn in the solar system. It is a highly evolved terrestrial planet. It's essentially, it's out of, you can't get it back in that shell, okay? It's evolved to a point where it's now got a massive CO2 atmosphere. It has no water vapor on its surface. It has no ocean. It will not be able to draw that CO2 down. So these sorts of evolutionary processes might be quite common out there. We might expect to see quite a lot of Venuses, and I'm sure Stephen will talk about that. So the other thing to point out is that even though Venus underwent that type of evolution, there may be different types of evolution for terrestrial planets elsewhere. And this is a fantastic video that was put together by Laura Schaefer and her graphic designer husband. I also have a graphic designer husband, so I'll point that out. And this is a great movie showing that, Earth has pretty much always been in the habitable zone, that blue river there, but you can see that Proxima Centauri, an M dwarf, actually started very much interior to the habitable zone. That means closer to its star than the habitable zone, in kind of the Venus zone. And so that means it underwent sort of Venus-like runaway, potentially, for about 170 million years before the habitable zone finally swept over it. And so the things we see benignly sitting there in the habitable zone around M dwarfs probably underwent some pretty violent early history. How violent was that history? Well, if we look at, this is the evolution of the habitable zone as a function of time, and what we're seeing here is that in a G dwarf, the habitable zone stays at roughly the same position over time, and we have, a gradual brightening of our star. For an M dwarf planet, though, essentially it starts out here very much interior to the habitable zone. This is kind of the dangerous popcorn region over here. So it starts out there and then evolves with time into the habitable zone. But you can see that the smaller the star, the longer it spends in that popcorn zone. And so when we look at M dwarf terrestrial planets, we're going to see things that have undergone a very different evolutionary sequence. So because of that evolutionary sequence, M dwarf terrestrials may have experienced a very early ocean loss. If you're subjected to Venus-like and above radiation early on, it's hard to hold on to your oceans and atmospheres under those circumstances. And so this plot here is kind of looking at atmospheric escape and ocean loss for different stars of different masses. And you can see in the M dwarf region, typically anywhere in the habitable zone of an M dwarf, you've lost at least one Earth ocean of water over time. The K dwarfs don't have as big a problem with this. The M dwarfs therefore have a problem. You think, well, that's okay, we'll just avoid looking at them. But the problem is that these are the first objects that we will study terrestrial planets around. So we can't avoid looking at them, so we need to be aware of these sorts of things. So if you lose an ocean of water, you can generate about 250 bars of oxygen as you fertilize that ocean and put it out there. So these ocean-lost planets may also, and this is a testable hypothesis, have high abundance oxygen atmospheres. Obviously, all 250 bars of that oxygen is not going to hang around, and there's been some great work by Robin Wordsworth, who's here as well, and Laura Schaefer, looking at the processes that will tend to draw down that oxygen and how much actually might be left behind. And so you may only end up with, say, a few bars of oxygen, or maybe even none of it in the case of Venus, for example. And so this is another major theme as well. If these things undergo massive evolution, what do we think their atmospheres might be like, and how do we think those atmospheres might change over time? And what this particular set of plots is showing is that three separate groups are now looking at sort of estimates for how many oceans were lost from the different TRAPPIST-1 planets, and we're all coming in within an order of magnitude of the same sort of results, which is that really you're looking at more than 20 oceans of water lost by TRAPPIST-1, B, and C. But remember, they're very volatile-rich. Maybe they have 20 oceans to lose. So, but again, very different processes, nothing like anything in our solar system. Atmospheric loss, of course, is a consideration. That may strip an atmosphere. As you fertilize things and you lose hydrogen off the top, you change the composition redox state of the atmosphere. But the thing to remember when you're losing stuff off the top is that an atmosphere is a system with stuff being lost off the top and stuff being replenished from below. And so it's not just enough to calculate atmospheric loss and say this planet will be stripped. You also have to take into account the fact that there will be outgassing from the interior of the planet as well, potentially, which will replenish that atmosphere. So those two processes will ultimately decide what the atmosphere is like. So Mars and Venus could help us understand these processes. Mars and Venus can help us understand both outgassing and atmospheric loss for that. Again, these evolutionary processes could generate uninhabitable, habitable zone planets. I showed you this plot earlier, and we kind of looked at this vertical column here. But if you now look at this line over here, this is kind of showing you that if you go Venus early on during that popcorn phase before the habitable zone sweeps over, that can persist. So it's like factory pre-installed carbon dioxide on your planet. Once you have that, and this is the range through here, and including the habitable zone region here, but all of these planets, if they have a dense Venus-like atmosphere to start with, do not become habitable again, and they have extremely high temperatures, even in the habitable zone and beyond. So evolution matters because it changes composition, and composition matters for climate. Okay, so M-dwarf terrestrial atmospheres might be oxygen-dominated, CO2-dominated, water vapor-dominated, especially if they are volatile-rich and they're outgassing, sort of a bit like a temperate Titan. We may see that sort of thing. Tidal locking can reduce spin-orbit resonances as well for these planets. So I've just transitioned, very abruptly from looking at sort of the atmospheres to looking at the other sorts of processes that affect habitability for these planets. So you've probably heard of tidal locking, and that is not always when the same face of the planet is pointing towards the star. It's a dynamical state in which you can end up in different types of spin-orbit resonances, including Mercury's 3-2 spin-orbit resonance. So yeah, when everybody said, oh, tidal locking, it means the same face will always point towards the star, we could, again, just look at the solar system and you point to Mercury and you say 3-2 spin orbit resonance. So we already knew that that wasn't always the case. But people have calculated, and this is a great paper by Rebus et al., European group, looking at, for Proxima Centauri b, what the probability was that it would end up in a particular dynamical state. So again, if you're locked to the surface of, if you're always pointing the same face towards the star, that can have climatic consequences, including sort of heating one side and cooling the other. But if you have an atmosphere or an ocean, you can potentially minimize those issues. But the one thing you want to avoid is having your atmosphere collapse out onto the night side of the planet, because if it gets too cold on the night side, you just condense CO2 out as frost and you just start losing that on the other side. So these are things we also have to consider, but again, we can observationally test whether or not these things are happening. And then finally, of course, we have all this dynamical doom and gloom, but many M-dwarf planets are in close-packed multi-planet systems and are interacting with each other, pumping up each other's eccentricities, and therefore potentially helping them avoid a true synchronous rotational state. So we'll have to go out and observe them and see what's actually going on. And then finally, of course, the importance of the stellar spectrum. that cannot ever be understated. The spectrum of the star drives the bolometric spectrum, the overall wavelength drives the climate of the planet, but the UV drives the photochemistry and photolysis. Extreme UV drives atmospheric escape. And so the star is really absolutely critical in all of this. And this is just a spectrum of the different UV from different types of stars here. You see it doesn't quite follow the linear scale you would expect. And this same wavelength region is a region where a lot of molecules are photolized. And so a lot of chemistry goes on and atmospheric compositional changes in that case. And this is just sort of an example of what happens in the planetary atmosphere. This is called a spaghetti plot. It's essentially showing the abundance of different chemical constituents in the atmosphere. This is their abundance. Their mixing ratio here is a function of altitude. What you need to see here is the way that these different lines in the same color actually move around this diagram, showing different abundances. And this is for a planet that has the same surface flux of gases, but is being modified by different ultraviolet spectra from the star. So this is already giving you a hint that when you're trying to interpret biosignatures on your planet, you're going to have to worry about what the stellar spectrum is doing, because it is a form of sync. It is a way of getting rid of some of these gases or enhancing their lifetime. And so without understanding what the star is doing, you can't really interpret what you're seeing there. So moving on from factors that affect habitability, so there are two paths we have before us to search for life on exoplanets. We have what's called the M-Dwarf opportunity to study habitable zone terrestrials orbiting M-Dwarfs in the near term, in the next 5 to 10 years. JWST and ground-based telescopes will go after that, and we'll have talks on that in the last day of this workshop. And then we're also moving towards a longer-term capability, which we might be able to start from the ground as well, but which will ultimately require space-based telescopes to do direct imaging observations of terrestrial planets. So from the ground and JWST in the near term, and potentially OST in the longer term, the Origin Space Telescope, we're going to be looking at M-Dwarf habitable zone terrestrials. That's the ones that I said have all of these interesting issues. You can think of them as problems, or you think of them as interesting scientific examples of different types of processes that will really enhance our understanding. So that's the way I like to think about them. So we will get to observe those first because of the simple fact that if you're a small planet, you can produce a bigger signal in transmission around a small star than you can around a large star. And since we are trying to observe things that are very difficult to see, that's great. And in fact, this TRAPPIST-1 star that was recently discovered is fabulous for this because it's actually not much bigger than Jupiter. And so an Earth passing of something not much bigger than Jupiter can have a very big effect on the light from the star. And so we're using this technique of transmission spectroscopy where the star backlights the atmosphere, and we look at the apparent size of the planet. When the atmosphere is completely transparent, the size of the planet is the solid size of the planet. But when the atmosphere has an absorber in it like water vapor, the planet appears to get bigger because now the atmosphere is also blocking the light as well as the solid surface. And so by doing that at a bunch of different wavelengths, we can actually track which molecules are in the atmosphere. So we'll use that technique. I just made it sound really easy. I just want to show this shot taken from the space shuttle of the thin blue line. This is the Earth's atmosphere. So this is what we are trying to measure in transmission spectroscopy, the difference between that big black circle and this little bit of extra stuff coming from the thin blue line. So don't ever think that this is going to be easy, but it's something that we're really excited about doing. The other technique we can potentially use is direct imaging. And so these are telescopes that we hope to build in the future, either large ground-based telescopes or telescopes in space that will allow us to actually pick out the pale blue dot of Earth and be able to take directly spectra from it. To compare these two techniques for astrobiology, I want to say that transmission is unlikely to probe the near-surface atmosphere simply because of the opacity of molecules and the effects of refraction as you're backlighting and coming through. So we're really studying the upper atmosphere, the sort of mid-troposphere of terrestrial planets with transmission spectroscopy. So we get no information on the planetary surface. We skim through the atmosphere above it. We don't see it directly. We're sensitive to higher altitude trace gases, and sometimes we get a longer path length than we do with direct imaging, so that can be an advantage. But the biosignatures we look for must be able to survive at higher altitudes. They must be fairly robust to photochemistry. In direct imaging, though, we get access to a terrestrial planet's deep atmosphere and surface because we're looking straight down into the planetary environment and potentially all the way to the surface, depending on clouds and opacity. Therefore, we get an improved habitability assessment of the surface environment, improved access to near-surface biosignatures. So for that reason, direct imaging is definitely something that's very desirable and out there to do. So as we search for habitability and life, there are 4 basic questions using these telescopes that we'll want to try and answer. So does it have an atmosphere? Number one, if it doesn't have an atmosphere, and again, Europa people don't at me, but if it doesn't have an atmosphere, okay, we can have the liquid water on the surface, which we need as astronomers to be able to remotely detect the life. So what is the nature of its atmosphere? Once we know it has one, what's it like? Can that give us some clues to what's actually going on there and whether or not it's habitable? Does it have an ocean? Can we just sense that directly or indirectly in some way? And are there signs of life? So these are the four main questions. So I'll just briefly go through sort of some of these to give you an idea of what people are working on right now. So this is astrobiology, and we're all trying to build the bricks of that pyramid to get us up to this detection of life. So does it have an atmosphere? With JWST, we should be able to go after the atmospheres of the TRAPPIST-1 planets, and two independent groups have shown that we really just need a handful of transits, watching the planet as it goes in front of its star and looking for those atmospheric signatures to actually tell whether or not an atmosphere is there. So I have high hopes that JWST will get us the first detection of a terrestrial planet atmosphere, if the ground-based people don't beat them to it. What is the nature of that atmosphere? Well, again, with something like the TRAPPIST-1 system and JWST, we can go after particular molecules. Carbon dioxide should be very straightforward. And carbon dioxide is an excellent indicator of a terrestrial planetary atmosphere. It is a totally crummy indicator of what happened to that atmosphere, because 365 parts per million of CO2 looks pretty much the same as 96 bars of CO2 as far as the absorption is concerned. So the absorption is so strong that it saturates very quickly, and so we can't really use CO2 as a discriminator. But if we see it, we know we're likely looking at a terrestrial planetary atmosphere. So and it's very highly detectable, strong features. So that's one of the first things we'll go after. We can also then look for whether or not it's in some kind of a post-runaway state, whether it has a massive O2 oxygen atmosphere, and we'll see that potentially via O2 collisionally induced absorption, which produces some fairly large features here. So this is 12 transits, TRAPPIST-1b, looking for this O2. And so we may be able to tell that this thing has undergone massive water loss and an ocean runaway. And then we can try and constrain outgassing from the interior, and potential habitability via looking for water vapor abundance and sulfur dioxide in the atmosphere. But that requires, quite a few transits, 125 in this case, which we might be able to glean out of the JWST mission if we get every single transit. So every single transit is our rallying cry for this. We can also potentially use larger space-based telescopes in the future to look at transmission spectroscopy of this system as well. With OST and LUVOIR could potentially do transmission spectroscopy of this object also. And then LUVOIR itself, so a larger, say 15-meter class direct imaging telescope in space, should be able to allow us to get very, very nice compositional measurements for atmospheres. So does it have an ocean? One of our final sort of questions that we want to ask. I originally thought this would be basically impossible, but as we work on this problem, putting our bricks down, we figured out a bunch of different ways that we could look for the presence of an ocean. So first off, JWST is going to be very good at looking at the presence of not an ocean. Okay, so JWST will be far better at telling whether an ocean has been lost than it will be at telling whether or not an ocean is still present. Water vapor, 125 transits, O2, 12 transits. Okay, so we will look first for loss and to see whether we can confirm that. If we see the O2, we might also be interested in trying to take some additional observations, but not many more additional observations, to try and look for, actually I have bars around this. There's the O2, and here we have HDO. It's possible, because we're going through the transit path, we can pick up things that are more likely to be trace gases. But HDO, heavy water, which is a fractionation effect that's formed when an ocean is lost, and we see this on Venus. For Venus-like HDO D to H fractionation, it turns out that maybe as few as 10 transits for TRAPPIST-1b, for example, could pick out something like this. So we can look for the O2. If that's gone and we're in a more Venus-like scenario, we can look for the D to H, the enhanced D to H ratio from atmospheric loss. So there's two potentially testable hypotheses that we could do. So that's inferring ocean loss. How do we actually detect whether there's an ocean there? Well, again, back to the solar system. So here's examples of direct imaging observations that have looked for oceans. So if you can see the glint up there off Kraken Mare on the north pole of Titan, and over here circled, if you can see that bright spot on the crescent of the Earth seen by the LCROSS mission as it went by, looped around the Earth before it finally had a suicide mission into the moon. In that case, you are a remote sensing ocean detector. This is glint coming off a liquid surface. And so we could potentially look for this on exoplanets as well. We will need direct imaging missions to do this. We will stare at that pale blue dot. We will not be able to see the continents on it. But if we take time-resolved observations as the planet hopefully rotates underneath our telescope beam, then we should be able to map the surface and essentially pull out different types of surfaces with different types of albedos and look at how the brightness or the reflectivity of those surfaces changes as a function of phase. And it turns out water has a very characteristic change in its reflectivity as a function of phase, which is part of what leads to that glint phenomenon. And so we might, with a large enough telescope, be able to go after direct detection of glint from an extrasolar planet. So finally, are there signs of life? So ultimately, this is what we're all here for. We want to try and find life out there and to address the question of whether or not we are the only genesis of life in the universe, or whether it has occurred elsewhere. So a biosignature, the thing that we're looking for is really just the way that life has globally modified its environment. So that's what we're looking for. We're looking for the impact of life on a planetary environment. And so we have a bunch, because again, we're looking with a telescope from 10 parsecs. We may not have the ability to actually discriminate what's going on the surface. We won't be able to see giraffes or narwhals or whatever is there. But we're hoping that we can see essentially the action of bacteria over billions of years acting on the planetary environment and changing both potentially its geology as well as its atmosphere. So the criteria for identifying a biosignature, when we think about, okay, what are the things that we should look for? We want it to be reliably produced by life, if that's at all possible, and less likely to be produced by other planetary processes, such as geology and photochemistry. We probably won't always get that wish because atoms are atoms, they're everywhere, and they interact, and there are processes that can put them together that aren't just life. We worry about its survivability, so you've generated this lovely complex, dimethyl sulfide molecule, and you've released it off into the atmosphere where it promptly gets zapped by the first UV photon that comes along and loses its methyl groups, and it's a mess. So survivability of that biosignature is also important. So you can generate it, but it also needs to persist in the environment and build up to detectable quantities without reacting with all the other things, including the biogeochemical cycles of the planet. It needs to be detectable as well. So the bottom line is we have to be able to see it with our telescopes. So can it build to detectable levels? Does it work for the telescopes we're building? Is it active in the observed wavelength region? And is it clear of any overlap with other common planetary species that would make its interpretation and the data analysis point difficult? Okay, so biosignatures, and this is a major theme. Biosignatures must be interpreted in the context of their environment. You can't just, as I said, all think, detect oxygen in an exoplanet atmosphere, collect Nobel Prize, all right? That was the way we thought about this. Not so long ago, only 20 years ago, I think. The new thing is it's a little more complicated than that. And you saw that diagram, planets are hard. And you have to understand that, again, life is a planetary process. It's interacting in that environment. It's changing things. It's being changed by that environment. And so when you see something in an atmosphere, you're going to need to understand all these other planetary processes as well. So some of the big questions facing us in biosignature science are, how do we discover new potential biosignatures, especially with those with higher probabilities of detection? We do have oxygen. We will go after oxygen. It will be the first thing we look for, but it will not be the only thing we look for. And so we're trying to come up with other things that we can look for there. And then finally, how do we increase our confidence in the interpretation of the candidates we do have? For things like oxygen, how can I be certain that that oxygen is due to life and not some other process? And so we have these sort of fundamental questions that are guiding a more comprehensive framework for biosignature assessment, which are, again, what does life produce? What are our biosignatures going to be? Can a dead planet fool us? So this is the concept of a false positive. Are there ways that photochemistry or geology could actually create the thing we're looking for? How do we interpret limited data? And this is not something I'm going to talk about, but there's some fantastic work being done by Sarah Walker and Sarah Johnson as well on how we essentially get at being able to put confidence, to be able to use what data we have and combine things from multiple fields to increase our confidence in what we're doing. And looking for false positives is one of those things, but also looking for things as networks or looking for anomalous patterns or just looking for things statistically over multiple samples. How are we going to do this? And how do we quantify our certainties? When we go to the New York Times or whatever, how do we say, well, we have, a 50% confidence that this is life, or an 80% or 90%? Could we even put a number on it? How do we transmit that confidence in what we see to the public and to ourselves? So just going to go through this briefly. Some classic biosignatures that you probably are aware of are things like the atmospheric disequilibrium biosignatures, which Josh Christensen-Totten is going to talk about on Friday. This is where essentially life has modified its environment by producing a surface flux of gases. And there's one thing, and I'm going to get into an argument with Paul, I'm sure at some point, Falkowski, about disequilibria, is that disequilibria can also be a sign of habitability. If a disequilibrium is there, it can be exploited by life to produce energy. But in the case of the global planetary environment, what we're looking for is something that is in disequilibrium, which means that there is an active flux of it in the environment. And it's us going after that flux and saying, what is that flux? And how abundant is it? How massive is that flux that helps us distinguish it from life or a geological process? So that's what we're really kind of looking at is disequilibrium tells us this flux. Does that surface flux exceed the rate for abiotic processes? Is that flux only due to life? And so from our planet, for example, a solid example is methane. It's produced at a roughly 60 to 200 times higher rate by biology than it is by the geology on our planet. And so you'd be looking for that flux differential to interpret things. For agnostic biosignatures, life is improbable chemistry. We're looking for patterns. For example, life tends to produce hydrocarbons in very quantized areas, whereas abiotic processes tend to produce hydrocarbons in a much smoother, more sort of analog situation. If you look at chemical networks, and this is again work done by Sarah Walker, if you look at chemical networks in the atmospheres of the planets, the Earth's network looks very different to that of Venus and Mars, and that is in part because of life in it. In fact, it looks more like a life type process. So as we work towards a comprehensive framework for biosignature assessments, again, biosignatures in the context of the environment, absolutely important, which means we need to understand that environment as well. And the false negatives, the inferred biosignature surface fluxes, how can we get at those and how can we get the right estimate? And then, of course, false positives. So what is a false negative? I've mentioned false positives, I haven't mentioned a false negative. So false negative is basically when the planet's environment, including its biogeochemical cycles, can suppress the buildup of a biosignature and make it otherwise unobservable. So oxygen is a classic example of that. And Tim Lyons is going to be talking about that at this workshop, is the history of oxygen on our planet is such that it may not have risen until only about 800 million years ago. And so during that time, the planet was essentially suppressing the rise of oxygen. So that's a concern because we could go looking at a planet that's got life all over it, but we won't be able to tell because it hasn't risen in its abundance. We can also get false negatives just from detectability issues. If we're looking for one of these more fragile, complex organic molecules that is photolized very rapidly, even down in the troposphere of a planet, then if we're looking through the upper atmosphere of the planet with transmission, we will not be able to detect that biological molecule that's sort of hugging the surface. And so we may not be able to get down and see those sorts of things. You should also know that the M-Dwarf spectrum can modify biosignatures. It can destroy them, and it can also allow them to persist for longer than, say, on a planet around a G-Dwarf. And so the example of that is there are some stellar spectra, some UV spectra, M4 stars in particular, that allow methane to actually build up, M2 stars, I'll have to read off that graph, that allow methane to build up in the atmosphere more than you would expect. And so when you see a methane abundance, you can't just say, oh, that would be consistent with biological flux. You have to say, okay, how efficient is the star at destroying that? Okay, I have to finish up here. I'm going into the red. I just see that. So photochemistry, as I said, if the methane builds up, then you actually get a much more prominent detection of methane in your spectrum. But again, you need to understand the fluxes and the destruction rates to be able to interpret what's going on. And just to show that, for a fixed abundance here, what we did is we fixed the abundance of the constituent in the atmosphere. We ran a bunch of simulations where, sorry, I keep missing that. We ran a bunch of simulations to say, okay, how big would the surface flux have to be for planets orbiting different types of stars, M2, M4, Proxima Centauri, TRAPPIST-1, to actually build up to the abundance that we see. And you can see that there's sort of nearly a factor of 10 difference in the abundances that you would need just depending on the spectral type. So maybe I've belabored that point, but the point is the star matters. We need to understand it. Okay, there are also a lot of false positives that are currently known, and Robin is the author of one of those. But the point is, briefly, that for all those false positives, because we understand the mechanism that creates them, then we can start to look for things in the environment that would give them away. So there could be telltale signs or discriminants that a false positive is acting. And I won't go over this diagram, but just to say, you know, when things are present or not present, they give us clues as to whether or not we're seeing an abiotic process or a biological process. This can then be used in observing sequences for missions, for both JWST, for example, and for the LUVOIR plans. So that can help us, actually looking for false positives can help us make our detection of oxygen more robust. And then finally, Venus may help us also understand false positive chemistry, and this is work being done by Mike Wong, who's here at the workshop today as well, and it's going to be presented by Jada in her talk. But, you know, Venus has rapid CO2 photolysis going on all the time, and that's one of the mechanisms that could potentially produce a false positive, and yet we don't see a false positive of oxygen on Venus. Why? We need to understand that, and so Venus can help us understand the catalytic chemistry that probably is causing that not to happen. So I'm going to skip over that, but just to say, again, environment's key. We need to understand false negatives, false positives, and finish with the astrobiology themes here. So astrobiology is necessarily massively interdisciplinary. All of these different studies, planet formation, even the origin of life and the environment in which that is created helps us choose the right targets. Coevolution of life, solar system, planetary evolution, all of that stuff. And remember that life is a planetary process. You probably won't be able to interpret the spectrum of the planet you're looking at if it has life on it and you ignore that fact, okay? So that's actually, you know, for those who say, well, planetary science is great. Yes, but if your planet has life on it, you also need the astrobiology to be able to do that. So detecting a biosignature is a potential first step, but you're going to need the entire field of astrobiology to actually help you interpret what you are looking at. So I will finish there. Oh, yeah, so that is kind of exact. Sorry, the question is, can I define what outgassing is? So outgassing is the release of volatile compounds, gases from the interior of a planet. So things like fumaroles, volcanic eruptions, that sort of thing. So essentially, gases from the interior are coming out into the atmosphere. Okay, and that's, you know, once you get your primary atmosphere, so your original hydrogen envelope is stripped off via either interaction with the star or via planetary formation processes. The atmosphere that we have right now, the one you're breathing, is a secondary outgassed atmosphere that's also been evolved and modified by life. So we would have had the hydrogen stripped, and then we would have outgassed CO2, water vapor, all these different nitrogen, all these different types of compounds. So that's what I mean there. Excellent question. Yeah, you can do secondary eclipse, which looks at the actual emission from the planet. For the TRAPPIST-1 planetary system, that will work best for the hotter planets, not quite so well for the ones in the habitable zone. And so I didn't go into that in as much detail, but that is absolutely something that we could go after. You could essentially also co-add the entire sort of mid-infrared spectrum and look at things like being able to detect whether or not there's an atmosphere there, also from phase curves. So not just from secondary eclipse, but actually just looking at the relative brightness or the temperature as the planet goes around in different phases. So yes, there are other techniques of doing that. I also didn't get into template matching for ground-based telescopes, which is another way we can go after oxygen in the near term. But Jared will probably talk about that in his talk on Friday. So yeah, there are a bunch of other techniques. I just concentrated on those two because they will be the primary ones that we will use. But for TRAPPIST-1, the transmission spectrum ends up, for the habitable zone planets, ends up being the most efficient. So yes, so the question was that, let me see if I can paraphrase this. The question was that given that we care about these things like false positives, true positives, you know, and basically getting confused by, I think, geological versus biological processes, what does methane on Mars essentially teach us about this? And so, yes, that's a very interesting problem, and so that's another one we're actually going after, and that's an analog, an in situ analog for exactly the sort of thing that we are going to be looking at with our remote sensing. We will detect something, and then we'll have to interpret it. So the methane on Mars, that was a detection. that was relatively fast. The interpretation then takes a very long time as we try and figure out, is this more likely to be a geological process based on its behavior, its temporal, its locality, its temporal behavior, what is scrubbing it out of the atmosphere? We still don't understand that. So there's a bunch of stuff going on there. But yeah, that's a really nice solar system analog for what we're going to hit as exoplanet scientists.